Let's bring it all together and build the core architecture of DAS 2.0. We have not talked about different types of RF signal sources. We'll do that after we complete the discussion of core architecture. RF sources are not part of a DAS, but without a signal source, DAS will not work. We mentioned RF signal travels through coaxial cable. Output of signal source feeds into a DAS via coaxial cable. You may remember signal loses its strength in a coax rapidly. So to distribute signal over a large area, we use fiber. Fiber only carries optical signal, so we need to convert the RF signal to optical signal. We use a converter to convert RF to optical. Different manufacturer produces converter with different features and names. So for now, let's just stick to the term converter. This converter also distributes optical signal to multiple converters which are strategically located at different parts of the building. In the DAS industry, this second set of converters are known as remotes. Fiber length between these converters can be anywhere from a few feet to hundreds of feet. In most cases, this fiber will be a single mode fiber with SCAPC or LCAPC connectors like we have seen in previous chapters. Remote converts the optical signal back to RF signal and sends the RF to antennas via coaxial cable. These coaxial cables will be ½ inch in diameter in most cases. Depending on how engineers want to split the RF, we may have a splitter or coupler between the remote and antennas. In most cases, multiple antennas will be connected to single remote. Let's introduce two more elements to this architecture. RF interface unit. This is quite common for all fiber-based DAS or DAS 2.0. Essentially, this unit receives the signal from RF signal source and feeds into the converter or distributor. Different manufacturers have different names for this unit. We'll take a look at those names soon. The next one is the DAS tray. If the output of signal source is too high, we need something to lower the power of the signal. In most cases, RF interface unit has a defined input range, and this input is low power RF, which is a few milliwatts to 3 to 5 watts. This is especially the case when the signal source is a base station. Base stations usually have high output power, and having 20 to 60 watt output is not unusual. We use a DAS tray in these cases. DAS tray takes the high input from base station and brings it down to the lower level that DAS can take. In this diagram, I have laid out elements of DAS 2.0 horizontally. In the next slide, I will present the same diagram, although a little simplified and vertically. We start with signal source which feeds RF signal to RF interface unit through the coaxial cable. In the last slide, we introduced DAS tray, but here I removed it to keep it simple. RF interface unit feeds the signal into a converter or distributor through coax. Converter converts RF to optical signal and distributes optical signal to multiple converters. These are remotes. I'm showing only one remote to keep the line diagram simple. Depending on the size of the building and need for coverage, you may have one to many remotes. Remotes convert the optical signal back to RF and send the RF to antennas via coaxial cable. Here too, depending on the size of the building and need for coverage, different remotes may be connected to different number of antennas. Again, this was the same core layout as the last slide, just presented vertically. You'll find out by next section why I laid this out vertically. It will help you understand the architecture of different DAS platforms. Please keep in mind, depending on the coverage requirement inside the building, DAS engineers goes through thorough engineering analysis to determine the number and locations of the antennas, remotes, and head-end electronics. We'll cover the basics of design process later in the course.